Find ID using LCM equations of this PMOS transistor. We are given that voltage threshold equals negative 0.4 volts, transconductance parameter equals 1 milliamp per volt squared, bulk threshold equals 0.2 volts to the 1/2, channel length modulation equals 0.1 volts to the negative 1, oxide capacitance equals 1.004 microfarad per centimeter squared, surface potential equals 0.88 volts, width equals 1 micrometer, and length equals 0.1 micrometers. So the first step, as always, is to identify the 4 parts of this MOSFET. We can see that on the left here, it is the gate. On the top, we have the source, as it is P-channel, and on the bottom is the drain. On the right side here, we have the body, or substrate in other words, which is connected to the highest potential of the system, which was given to be 3 volts. So, off the bat, we need to see whether or not this device is on. We need to find VSG and see if that is greater than negative VTP, which includes VTP0, but also accounts for body effect. So VSG equals VS minus VG. And at node VS here, we have 2 volts. At G, we are at ground, which is 0 volts. So the difference is only 2 volts. To see if there's body effect, VBS must be a non-zero value. And of course, that equals VB minus VS, where the body's at 3 volts, and the source is at 2 volts. 3 minus 2 volts is 1 volt. Since it is not 0 volts, we must account for body effect. Therefore, body effect exists. Now to find the adjusted VTP, that equals VTP0 minus gamma times parentheses square root of absolute value 2 phi f plus VBS minus the square root of absolute value 2 phi f again. Plugging in the values, we put in negative 0.4 volts minus gamma, which is 0.2 volts to the 1/2. Multiply that by square root of 0.88 volts plus VBS, which we found to be 1 volt, minus square root of 0.88 volts again. Putting this in the calculator, you get VTP equal to negative 0.487 volts. Remember, it's P-channel, so it has to be negative voltage threshold. Comparing this with VSG, which we found earlier to be 2 volts, that is obviously greater than the negative value of VTP, which was 0.487 volts. Therefore, the device is on. Now, to see what mode it's in, we need to find the value of VSD sat. And if VSD is less than this, it's in triode or linear mode. And if it's greater than this, it's in saturation mode. Given LCM equations, VSD sat equals VSG plus VTP. That's it. And that equals 2 volts minus 0.487 volts, since you're adding a negative number. And that equals 1.513 volts. VSD, on the other hand, equals the usual VS minus VD, which is 2 volts minus, down here, this node is 1 volt. And that equals 1 volt. So comparing these two, VSD equals 1 volt, and that is obviously less than VSD sat, which equals 1.513 volts. So we can confidently assume that this MOSFET is in triode region. Now for the final formula, we need to find ID, which I'll denote a little tri here for triode, which is along the right side of this MOSFET, which I'll call ID. This equals Kp times parentheses VSG plus VTP times VSD minus VSD squared over 2. And this equals 1 milliamp per volt squared, which is the same thing as saying 1 times 10 to the negative 3 amps per volt squared to get it in constant units. Take that and multiply it by the following. VSG is 2 volts minus VTP, which was negative 0.487 volts, times VSD, which was 1 volt, minus VSD again, squared over 2. This will give you your final answer of 0.001013 amps, and converting that to milliamps, that's 1.013 milliamps. Pretty small amount, but reasonable nonetheless. And that's everything. If you have any questions, please leave in the comments below, and good luck.